Hello,
Hello.
am I audible?
Yes, sir.
And is my screen visible to you?
Yes, sir.
Okay, thank you. So, good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL PMRF TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraja. He is a professor in IIT Delhi. So, we have a 12-week course, and in the previous 11 week, we have completed most of the topics related to the probability theory and statistics. Okay, now this is the last week of the 12-week course. That is, we are in the 12th week. Okay, so up to this week, we have discussed about lots of things. Like in probability theory, we have already discussed about the basics as axiomatic definitions of probability, Bayes theorems, conditional distribution, conditional probability. Already we have discussed about random variables, discrete and continuous types of random variables, distribution function, density functions, inequalities, and the standard discrete and continuous distributions is there. Transformations of random variables are there. Okay, there are lots of things we have already discussed. Okay, in probability theory. And in statistics, that has started from week 9. Okay. In week 9, we have like discussed descriptive statistics. Okay, descriptive statistics and the sampling distributions is also there. That is T, F, and chi-square distributions. And then we have discussed about the point and interval estimations in the 10th week. Okay, in which we have discussed about the different methods of estimation, like maximum likelihood estimation methods. And in the last week, that is in the 11th week, we discussed about testing of hypothesis. Okay, that is also a part of the statistical inference, actually. Okay, so now this is the 12th week. Okay, this is the last week of the course. And in this week, we will discuss about the correlation and regression. Okay, so this is our, this is week 12. Okay, in this week, we will discuss about the analysis of correlation and regression. Okay, so like first we will discuss about the introduction related to the like what is correlation and what is regression. Then we will discuss about Pearson's correlation coefficients, Carl Pearson's, or this is also called linear actually. Pearson's correlation coefficient. And then we will discuss about Spearman's correlation coefficients, which is also called like monotone. And then rank correlation is there. And then we will discuss about multiple correlation and partial correlation. Multiple correlation and partial correlation. And then We will discuss about regression analysis. And at last, we will discuss about logistic regression. Okay, so this is the course, okay, of 12 week. So let's start with introduction part. Okay, since it is a very large class, there's a lots of topics is there. So I'm just putting some of the notes, some of the screenshots here, and we will discuss about these things. If anyone have any doubt, then he or she may directly ask. Okay, these are already covered in detail by Professor S. Dharmaraj. So I suggest you please watch the videos of all the topics, even not even for the regression and correlation, but all the topics related to the probability theory and statistics. Okay, we will just take some recap of those topics and then we will solve some numericals. Okay, so let's start with the introduction. So let's start with first correlation. What is correlation? Actually, we will discuss about the correlation. That means there is a relationship. Okay, and which type of relationship is there? So there are maybe there are two or more than two variables is there are there. Okay, so they are like associated with each other, or the one variable is dependent on the other variable. Okay, so there is some association between those variables. Okay, so from there, we have a logic or concept of correlation. Like here, the basic role of covariance is the we have already discussed about the covariance actually. Okay, if you people remember, covariance. Okay, let me write one formula first. The correlation coefficient is defined as like covariance between the variables, and it's divided by the sigma x sigma y, which is the standard deviation of the variables. Okay, the product of the standard deviation of the variables. Okay, so this is the correlation. So actual correlation coefficients is related to the covariance. Okay, so there is covariance between the two variables. Okay, so it is like we have already defined the expected value of xy minus expectation of x into expectation of y. Okay, so these are the quantity. That is, these are the like cross moments, expectation of xy minus expectation of x. That is the moment, first order moment of random variable x and first order moment of random variable y. Okay, so we these are already we have discussed. So covariance is actually based on the expected value of these. That means it is a scale variable. Okay, it measures it has some scale changes. So, but correlation coefficient is a ratio. It is a ratio of the covariance with the standard deviation of the two variables. Okay, so it is a ratio. Okay, it is a measure, a ratio, a proper a number is there actually, not natural number, a real number lies between -1 to +1 is this, which measures the uh, linear association between two variables. Okay, so like covariance also identify the nature of dependence. Nature of association is also evaluated with the help of covariance. Okay, but since it is like dependent on the scale of observations. So we formulate a formula like correlation that is derived by Carl Pearson. Okay, so he gave the formula which is independent of those scales, and that is measures the dependencies between the two variables. Okay, so and named it like correlation coefficients. Okay, and the correlation analysis is the study of analyzing the strength of such dependence. Okay, so if here you can see, if here you can see like the study of analyzing the strength of such dependence between the two random variables using the correlation coefficients. Okay, so with the help of those correlation, we check the degree of association between the variables. That means how much changes in one variable will impact on the other variable. Okay, so this is done with the help of the correlation. Okay, on the other hand, the regression analysis is there. So the regression analysis is what is concerned with the problem of predicting a variable. Okay, so there are two type of variable in regression analysis. The one is dependent variable and the other is independent variable. Okay, so there are two variables, the dependent variable and the independent variable, and we formulate a model that is how the sorry, how like the dependent variable uh, depends on the independent variable. Okay, how the changes in dependent variable impact the independent variable, and these are like similar, but since in correlation the both the variables are independent. Okay, they are not dependent. There is only a association between those variables. Okay, correlations are symmetric in nature. Okay, so like we can write covariance. Sorry, we are discussing about correlation. So correlation between the variable, correlation coefficient between the variable x and y equals correlation coefficient between the variable y and x. So both the variables are independent here. Okay, and we just measures the linear association or the association. Okay, or the association between the one variable to the other variable. Okay, but in regression analysis, we can we make a model to predict a variable. Okay, to predict the variable, and those variable that is predicted on the basis of the another variable. So it's called dependent variable, and the another variable is explanatory variable or independent variable. Okay, we will discuss about this. So it the correlation coefficient gives the uh, strength of association, strength of linear association between the variables. Okay, but not only linear, it may give the non-linear or monotone in nature, like here Spearman's correlation coefficient is there. Okay, so that gives the association between the variables. Okay, also the okay, we have already actually here. Okay, so there are mainly two types of correlation coefficient we will mainly discuss. Okay, uh, like the first one is Carl Pearson's correlation coefficient, which is also linear correlation coefficient is also known. Okay, so this is given by rho xy. Okay, it is rho is the symbol for the correlation coefficient, and the correlation coefficient is defined as the covariance of xy or divided by sigma x, rho x rho y. Here rho x and rho y is nothing but the standard deviations of the random variable x and y. Okay, and once you put the values like covariance of xy summation expectation summation of xi minus x bar multiplied by yi minus y bar, and the denominator is under root of summation of xi minus x bar whole square yi minus y bar whole square, and both have their like numerals like 1 by n is there, and after simplification this is the formula for the correlation coefficient for Pearson correlation coefficient. Actually, this can also be like written in the another form here, s xy divided by under root of sxx into under root of syy. Okay, here sx is summation over xi minus x bar whole square, the same thing actually. Okay, we just simplify those things, so we can directly use one of the formula or one of the form of the correlation coefficients. Okay, the correlation coefficient have some properties. Okay, it has some properties although okay, like it ranges from -1 to +1. Okay, so it ranges from -1 to +1. So that means if we have going to calculate the Pearson's correlation coefficient, then the value must be lie within the range of -1 to +1, including both. And sorry, and also any value that that is negative in nature, implies that there is a inversely relation between those random variable. There is an inverse relationship between those variables. That means if one variable is increasing in nature, then the other one is decreasing in nature. And if there is a positive correlation in between those variables, then that means both the variable are changes in the same direction simultaneously. Okay, so this is the Pearson's correlation coefficient. And also there is like the square. Okay, the square of the correlation coefficient is termed as coefficient of determination. Okay, coefficient of determination. So there are two type of like just wait for a minute. There is someone. Sorry for the disturbance. Am I audible? Hello.
Yes, sir. Yes, sir.
Okay, okay, thank you. Okay, so where we are? Okay, so the square of the correlation coefficient is coefficient of determination. Okay, so these are the terms. Then let's discuss about one numerical is there actually. So let's solve this numerical. We are given the data, the random variable. Okay, we are given the random sample x and y, and we need to find the correlation coefficient and coefficient of determination. So, okay, let's start. So, sorry. So, like we are given the random variables. Okay. So first we need to find like the formula is there. X bar is there. Y bar is there. Xi minus X bar is there, or Sxy. These are the terms we need to calculate. So let's start with the calculation. So here X bar. X bar is nothing but summation of Xi divided by n. Here xi, that is I from 1 to, there are six values actually. So 1, 2, 3, 4, 5, six values is there. So n equal to 6 here. Okay. So the summation of xi's are like 30 plus 32 plus 34 plus 36 plus 38 plus 40. And it is divided by 6, which comes out to be like 7 into 3, 210 divided by 6. Okay, so comes out to be 35. Similarly, you can calculate y bar. It's a simple calculation, just a calculation. Okay, so the summation of y bar, summation of yi divided by n. Again, the same 1.6 plus 1.7. You need to sum those. Okay, so it comes out to be it's 15.3, and it's divided by 6. And after simplification, it is 2.55. Okay, so these are the term x bar and y bar. Also, like the correlation coefficient. Okay, so we need to like calculate these also. So here like s x x is summation xi minus bar, x bar whole square. Okay, so if you can see x bar is 35 is there. So if you like 30 minus 35 is 5 is there. So 5 square is 25. Okay, 25 is there plus 32. That means 33. 3 square is like 9 is there plus 34. So 1 square is 1. 36. So again 1 square is 1. Then 38 minus 35, 3. 3 square is 9 is there. And then 40. Then 40 minus 35, 5. 5 square is 25 is there. Okay. So this is after summation like 10, 10, 50. Okay, it's 70 actually. So the SXX value is 70. In a similar manner, you can calculate SYY is there. So it is like 0.9025. Just you can solve. Okay, it's 2.55 is there, and 1.6 minus 2.55 whole square comes out to be 0.9 9025. Then it is like 0.7225, then 0.0025, then 0.0625 plus 0.4225 and plus 0.9025. Okay. And once you are able to calculate or simplify, you will find 3.015. Okay. So we have calculated these. And again, the last one, the SXY, which is summation over xi minus x bar and yi minus y bar. And once you are able to like simplify these as well, you will find 14.3. Okay. So let's calculate the rho xy, which is a correlation coefficient between the random variables x and y, which is like xy, xx, sorry, yy, its power half is there. So it is like 14.3 divided by under root of 70 into under root of 3.015. Just we need to simplify these things. 14.3, it's 14.529, which is rho xy is 0.987. Okay, so okay, the rho is here is like positive. So that means there is a positive relation. Okay, that means if the random variable x is increases, then the random variable y also increases. Okay, and since it is near 1, so that means it is highly correlated. Okay, so if you can see, both are like the numbers even, as the number increases 30 to 32, 32 to 34, 34 to 36, the y variable also increases, if you can see. Okay, so both are increases in the same direction. One is increasing, then the other one is also increasing. Okay, also there are highly correlated in nature. Okay, so that means since the correlation coefficient is near +1, so that means they are highly correlated. Okay, so we can interpret these values like this. Also, we need to calculate the coefficient of determination. We need to calculate the coefficient of determination, which is also nothing but the square. Sorry. So rho square is defined as 0.987 whole square, which is approximately 0.968. Okay. So that means like we are able to predict the change in one variable, impact the change on the other variable, which is around 96%. Okay. So that means if one variable is changing, the changes in one variable, then the 96% it can change in the another variable. Okay, 96.8. I mean, okay. So this is the coefficient of determination means. Okay. So is there any question till this point? Then you people may ask, or let's go to the next slide. Okay, now, okay, we have already discussed these things, but let's discuss one more time here. Okay, here like from Squart's inequality, it follows that the value of rho is lie within -1 to +1. Okay, here like if rho equal to 1, then this means perfect correlation. So perfect positive correlation is there. Perfect positive correlation. Okay. And in case if suppose like rho equal to -1 is there, then again it is a perfect correlation, but it is negative. Okay, perfect negative correlation is there. Okay, and what if rho equal to 0? So there is no linear dependence. Okay, no linear association. So there is no linear association if the the correlation coefficient of the random variable is 0. Okay, so there is no linear association. So like here we can see from the curve actually, if you are like able to see, like here we draw a straight line and all the points also like in the straight line. So that means all the points and the curve and the line also like perfectly overlap on each other. So that means it is a like highly correlated. Okay, perfect correlation is there. And since the one variable is increases, then the other variable is decreases. The curve is in like negative slope. So that means here the correlation coefficient value is -1. Okay. In a similar manner, like you can see the one in increasing, then the other one is also increases. So in that case, like, okay, so both are increases in the same direction. So here the correlation coefficient is +1. Uh, Also, there are scattered plot. Okay, and the scatter plot indicate which type of like correlation is there. So here you can see that the scatter plot is like not a line on the single line, but it is like scattered in within a region, but it gives us a trend that it is like decreasing in nature. Okay, so that means there is a negative, the negative correlation. Okay, and in a similar manner, like if suppose there is not a points lying on the same line, but it shows a trend of positive. So there are positive row, and also the last case is there. Okay, the last case where like there is no association we can able to like observe. So this kind of is there is no linear association between the variables. So this is called as no correlation between the random variables. So rho equal to 0. Okay. So okay. The next is like up to this point we have discussed about Pearson's correlation coefficient. Now we will discuss about Spearman's correlation coefficient. Okay, Spearman's or monotone. Okay, so the definition is like the Spearman's or the monotone. The monotone correlation coefficient of x and y is denoted by this rho superscript s xy. Okay, like this. Okay, sorry. The correlation coefficient, the Spearman's correlation coefficient between the random variable xy is actually rho times the u1 into u2. Okay, rho times the correlation coefficient times the u1 into u2, where the random variable are like continuous in nature, where these random variables should be continuous in nature. Okay, and u1 is like fx and u2 is like fy. That means these are like CDF of the random variable x and y respectively. And it is obviously we have already like learned this, that the CDF is uniformly distributed, uh, like sorry, here the CDF is like uniformly distributed between the random variables 0 to 1, and here it is again the same. And the reason behind the definition of the uniform correlation is based on the fact that it two uniform random variables are monotonic in nature. Suppose we are given the two uniform random variables are monotonic dependent. Okay, either positive or negative. That is another thing. But if there is a monotonicity present in the two random variable, then they are linearly independent. Dependent. They are linearly dependent. Okay, and thus, with the help of the transformation between the variables, their monotone depends becomes the linear dependence. Okay, so this is the reason Spearman's use the u1 into u2 as a weight, or we can say that as a linear coefficients, you can say. Okay, so this is the linear Spearman's correlation coefficient. Okay, then the next is hypothesis testing. Hypothesis testing of the correlation coefficients. Okay, of correlation coefficients. Okay, so thus we first construct the null and the alternate hypothesis. So the null hypothesis is like the correlation coefficient between the random variables is zero. That is, both are uncorrelated random variables. Against the alternate hypothesis is either they are positively correlated or they are negatively correlated, or there is correlation exists between the those random variables. Okay, and here we can see that like it fall the the test statistics actually. Okay. The test statistics, first we need to define, first we construct the hypothesis, and then on the basis of the given data and for the testing purpose, we define the test statistic. The test statistics here is T, which is like the correlation coefficient divided by the standard error of the correlation coefficient. Since we are using R here, okay, not the rho. Rho is the population correlation coefficient. Okay, and R is like a sample correlation coefficient. Okay, and rho is like population correlation coefficient. Okay, so we have defined a statistics because we don't know about the parameter value. Okay, the population parameter, the rho is not known. So we test those with the help of the sample correlation, that is R. So T equal to R divided by the standard error of the R. And this follows a T distribution, obviously, with the n minus 2 number of freedom, degree of freedom actually, if you can see. Okay. Also here, the R, the value of R is calculated by the same formula. Here, like R is calculated as XX, the data from the sample, we have calculated R with the help of these formula or the above formula that we have already mentioned in the above slide. Okay, sxy under root of sxx into syy. Okay, so from here, with the help of the sample, we calculate the sample correlation coefficient, and the standard error is also there because the standard error of R is defined as like 1 minus R square divided by n minus 2. Okay, so this is the standard error for the sample correlation coefficient, and the sample correlation coefficient is discussed by the R equal to the form, the given expression. This T follows actually T distribution with n minus 2 degree of freedom. Okay, so this is the how we proceed the test. Okay, once we are able to calculate the T statistic, then with the help of the given degree of freedom, we compare the calculated value with the help of the tabulated value from the T distribution, from the T table actually, and then we make our statement or conclusion related to the whether we are reject the null hypothesis or we fail to reject the null hypothesis. Okay, so okay, this is the case, and then we have one question actually. Sorry, we have one question actually here, like Okay, so the question is like the data in table, just the below table were obtained in a study of a relationship between the weight and chest size of infant at birth. Determine the sample correlation coefficient. Okay, we need to determine the sample correlation coefficient R, and then test the null hypothesis that rho equal to 0 against the alternative rho is not equal to 0 at 0.01 level of significance. Okay, so we need to calculate this. So let's start. Since we are given, so we need to like calculate the first, we need to calculate the R here. We need to calculate the sample correlation coefficient, the first step. Okay, so the sample correlation coefficient is like the formula is like SXY, SXX, YY. Okay, and how to calculate these values? So these values are calculated with the help of the table. So let's make the table here in the next page. So we are given what we are given. X is the weight in kg and Y is the chest size in centimeter. Okay, so we are given X in kg. This is the weight. We are given Y in centimeter. It's the height. Okay, so we are given like 2.76, 2.17. Okay, 5.53, 4.31. So it is like 5.53, 4.31. And then it's 2.30 and 3.70. So it is like 2.30 and 3.70. These are the weight of 6 infant. Okay, and the corresponding height is like 29.5, 26.3, 29.5, 26.3, 36.6, and 27.8. So it is like 36.6, 27.8. It's 28.3, 28.6. Okay, 28.3, 28.6 is there. Okay, so these are the values we are given. Now we need to calculate these value as xy, and that is defined as the summation over x xy. So obviously we need to first calculate the x bar actually. So the x bar is like summation xi divided by, we are given 6 values, 6. So uh, 2.76 plus something. So once we are able to like sum up, it is 20.76 divided by 6, and which is approximately 3.46. Okay, and similarly y bar is also there, which is summation over yi divided by like 6. So summation over yi is like 177 point like 06 divided by 6 comes out to be 29.51. Okay, so these are the x bar and y bar. So we need to calculate now xi minus x bar into yi minus y bar is there, and then we need to calculate like xi minus x bar whole square, and at last we need to calculate yi minus y bar whole square. Okay, here like we need to calculate the sample correlation. For that we need sxy, which is summation of xi, summation of xi minus x bar into yi minus y bar. Okay, so these are the table. Now we need to fill it. So I have already written it down actually. So it's 0.007, then it is 4.141, then it is like 14.676 is there, then minus of 1.453 is there, then it's 1.404 is there, and then it's 0.218 is there. Okay, and then xi minus x bar whole square. So it is 25, sorry, 2.76 minus something 3.46. Okay, so it's 0.49 is there, then 1.664, then 4.285 is there, and then 0.722, it's 1.346, and then 0.058. Okay, so like we calculate the xi minus x bar whole square and xi minus x bar into yi minus y bar. Now then the next is yi minus y bar whole square. Okay, so that is 0. The first one is because 2.29.5 is there and the average value is also 29.51. So obviously it gives 0. Then 10.304 is there. It's 50.286. Then 2.924. It's 1.464. And at last it's 0.826 is there. Okay. So the next step is to calculate like summation value. Okay, so summation or SXY is there. So once you are we have these value, we can able to calculate. So it is like SXY is there. So SXY is the third column, the sum of the third column, which is 18.557. Just we need to sum those values. Okay, we will find out 18 point something. Okay, and then SXX is also there, which is 8 point like 565 is there, and SYY is here like 65 actually 65.788. Okay, so we have R. So the next step is to calculate R, which is the ratio of this, which is 18.557 SXY divided by under root of like 8.565 under root of 65.788. Just use calculator or some software to solve this. You will find out 0.782 is there. Okay. So that means 78.2% correlation exists between those data that we are given. Okay. The X, the weight. Actually, the question is like the weight in kgs and the chest size in centimeter of infants. Okay. So there are 78% like association between those data. Now the next step is to test. Okay, so here our the testing mechanism is like H naught such that rho equal to 0 against the null alternate hypothesis H1 equals rho is not equal to 0. So we need to check this. So we are given 6 values. Okay, we are given 6 values of X and the corresponding 6 values of Y. Okay, so we need to first calculate the T statistic, the test statistic, which is like R divided by SC. Then it is SC equal to under root of 1 minus R square divided by N minus 2. So just simplifying. So it is N minus 2 under root. It's R upon under root 1 minus R square. So this is the calculated value of test statistics. Okay, putting those values of R and N equal to 6. After simplification, we will get 2.509. Okay, and since we are given in question the level of significance is 1%. Okay, 0.01. So in the T table at 0.01 level of significance at 4 degree of freedom, because there are 6 values are given, so the degree of freedom is n minus 2. Okay, because there are two sample values involved actually, X bar and Y bar is involved in this calculation. So there are loss of 2 degree of freedom. So 6 minus 2, that is 4 degree of freedom is there. Okay, so there are 4 degree of freedom. So T value at 4 degree of freedom at 0.01 level of significance. This value, the critical value is like 4.604. Okay, so obviously, if we make the table like this, or the curve even, if we make the curve, suppose these are the values. So these are like 4.604. These are minus 6 point, sorry, minus 4 point actually. Minus 4.604 is there. These are the critical point, and these are the critical reasons actually. The critical reasons is this one, where the null hypothesis is going to be rejected. And our the calculated value is 2 point something. Okay, so that means our calculated values lie somewhere here or some other places, like 2.509. So it is actually reason of your acceptance reason. Okay, so that means we like not going to reject the hypothesis. So that means we fail to reject the null hypothesis. Okay, so we fail to reject the null hypothesis on the basis of the data that are given in the table 6.3. Okay, so is it, I think, clear up to this point? Is there any doubt to anyone?
No, sir.
Okay, thank you. Okay, then the next topic is rank correlation. Okay, up to this point, we have discussed like the correlation coefficients. But now, what if there are ranking systems in our data? Okay, so like we know that the ranking is the process of assigning ordered label, like the first, second, third, fourth, or the one, two, three, four. Okay, so these are the rankings. Okay, a ranking or ordered set of data. Okay, so etc. to a various observation of a particular variable. Then in statistics, the rank correlation is a measure of this ordinal relationship. Okay, so the above one is like we are given a continuous data, the random variable x and the random variable y are continuous random variable. Okay, and here, but here the rank correlation is mainly used for the ordinal relationship. Okay, and it measures the degree of association between the rankings of the random samples. Okay, it measures the degree of association, degree of correlation between the rankings of those random variables. Okay, so one such correlation coefficient is Spearman's correlation coefficient. Okay, the there are many rank correlation coefficient is there. The Spearman correlation difference correlation coefficient. Okay, so this is calculated with the help of this formula actually. Okay, so like here R, it is denoted by capital R. Capital R is the Spearman's rank difference correlation coefficient. So there is a ranking difference between the random samples of those random variables, and with the help of those ranking differences, we are able to calculate the rank correlation coefficient. The formula for this is like 1 minus 6 times of summation of di square. Okay, summation of di square. Okay, and it is divided by like n square minus 1. Here the di square is like okay, xi minus yi. Okay, suppose we are like the x random variable, y random variable is there. Okay, it has value. Suppose I'm giving the 3 or 4 values only: 4, 5, 2, 7. Okay, and it is like 14, 17, 11, 8. Okay, so we assign the ranks in those numbers actually. Okay, so like there is a rank. So the rank is like here, the rank 1 is for the 7 because 7 is the largest number, the greatest number. Then it's 2, then it's 3, then it's 4. So it's ranking R1, suppose, or XR1. Those are the any notation we can use. Okay. And the here the first rank is for 17, then the for 14, then this, and then this. So DI is what? DI is there is 3, there is 2. The difference is 3 minus 2. comes out to be 1. Here the 2, it's d1 actually. It's d2 is like 2 minus 1 equals 1. Then 4 minus 3. D3 is like 4 minus 3 equal to 1. And then d4 is like what? It's 1 minus 4 equal to minus 3. So there is a relation, there is a rank, like the difference between the rank, the corresponding rank of the random samples of the random variables. Okay. So this is the formula. We have one numericals actually on the basis of this formula. We will solve after we when we completed this task. Okay, so this is the correlation coefficient. We rank the random samples and then take the differences between those corresponding random samples. And with the help of this formula, we are able to calculate the rank correlation between those random variables. Okay, this gives the ordinal relationship between the ranking. Okay, now the next is multiple correlation. So up to above point, we are discussing about only two variables. Okay, there is the correlation between the two random variables. That is, one random variable is like correlated with the another random variable. But now there are more than one variable there, na? Okay, so there we can use like multiple correlation. Okay, like suppose we have three random variables, x1, x2, x3 are three random variables. Okay, so we are like we can able to calculate the one dependent variable is there, and there are two or more independent variable is there. Okay, because we need to calculate with respect to one variable. Okay, so for the sake of simplicity, we call them it as like dependent variable. So here like x1, we have taken x1 as dependent. Since we are taking three random variables, so x2 and x3 are independent. Okay, so we first like derive a linear regression equation. Okay, we derive a linear regression equation, which is like we need to calculate x1 because x1 is a dependent random variable. Okay, so the x1 is dependent on the x2 and x3, and up to what extent it depends on x2 and up to what extent the x1 depends on x3. These are like denoted by some numbers actually. So these are like 1 3.2 is there. This is like 1 2.3. Okay, sorry, 1 2.3 is there, and there is 1.23. Okay, so this is the like regression, linear regression equation, which is suppose one. It is already here actually. It is already here. 6.6 equation is there. Okay, so here A is the correlation coefficient. B is also, sorry, the regression coefficient or the correlation coefficient, whatever you say. Okay, so it is actually partial regression coefficient because here A 1.23 is there. Okay, here 1.23 is there. So that means the correlation. Okay, let me write here first. If you are able to like read this, you can find out. Here aij dot k denote the slope of line between the random variable x and the j. 1 2, that is x with j, the slope between the line x and j, x1, sorry, x1 and j xj, when xk is treated as constant. Okay, or we can say that aij, sorry, here a1j dot k. So here as a partial regression coefficient of 1, because 1 is the dependent variable. So we need like it is a partial regression coefficient of 1 on j when k is treated as constant. Okay, k is treated as, sorry, k is treated as constant. Okay, so in this scenario, we can write a one j dot k. That means the correlation between 1 and j when k is taken as constant. Okay, and the first one is like here, a 1.23. So the correlation coefficient of 1 only. Okay, so this implies a multiple correlation coefficient of the dependent variable 1 with respect to 2 and 3. So this is the multiple correlation, and there is partial correlation also. That means 1 with 2 when the third is taken as constant, A12.3, and the next one is A13.2. That is the correlation, sorry, the partial regression coefficient between the variable 1 and 3 when 2 is taken as constant. Okay, so this is the like multiple correlation. There are more than two random variables exist, and so there are multiple correlation is there. Okay, so there comes the partial regression is also there. So this is how we deal with those things. Now the next is the here following the same approach of least square approximation. Okay, as we use for simple linear regression, we can obtain the coefficient of partial regression. Okay, let n is the number of total number of observation is there. So if you can see, we have like what, xi equal to a. We are given this question actually. Okay, sorry, we are like x1, the dependent variable a 1.23 is there, plus a 12.3 x2 plus a13.2 x3. Okay, so this is our question. 6.6 equation is this. Okay, so this is our simple linear regression model. Okay, and then we need to calculate these multiple and uh, partial coefficient. Okay, multiple and partial regression coefficients, that is A1.23, A12.3, and A13.2. These are the terms we need to calculate. So for using the least square approach, least square approximation approach, we first make the normal equations with the help of these. Okay, and these normal equations are like very easy to calculate. Okay, like easy to form. So here we are given this equation. Okay, just take the summation on equation number 1. In equation 1, take the summation. So xi is like, sorry, x1 is summation x1 equal to a1.23 is there. Okay, so summation a1.23, okay, plus a12.3 x2. Since actually a1 dot, okay, so A12.3 is a constant. So A12.3 and then summation over x2. And the last A13.2 summation over x3 is there. Okay. The simple. So this is one normal equation. Okay. Also, since A1.23, here if you can see, A1.323 is a scalar or a constant number. So n number of time it repeated, so n multiply. So that is also like written as like this form. If you can see, A1.23 into n, because it is repeated n number of times because we have chosen n observation. Okay, so this is the first equation. Okay, I'm writing A, equation A, suppose. Okay, this is the first normal equation. The second one is, in equation 1, we multiply with the other two random variables. Okay, the other two random variable except x1 is x2 and x3. So first multiply by x2 in equation 1. Here you can see them multiplying by x2 in equation 1 and then taking summation. So that is what? So that is actually we are taking summation x1, x2. So x1 multiplied by x2 and then taking summation is equal to what? A1.23 summation x2 square. Okay, because sorry. Yes, x2 square. X2, not x2 square. Na? X2 is there only. Na? The first term is. Then A12.3 and then summation x2 square and then plus a13.2 summation x2, x3 is there. Okay, the same approach is multiply with x3 in equation 1 and then taking summation. The summation x1 x3 equal to a1.23 summation x3 is there plus a12.3 summation x2 x3, and the last one is a13.2 summation x3 square. Suppose I am taking c. So here the equation equation a, b and c is the normal equation. With the help of these three normal equations, we are able to calculate the three regression coefficients a1.23, a12.3, and a13.2. So we have three variables. That means we have three unknowns and we have three equations. So we are able to calculate with the help of this system of linear equations. Okay, so from there we can calculate the partial regression coefficients. Okay. The next is the standard error of these partial correlation coefficient. Okay, so following is the same approach as in the simple linear regression. The standard error of the estimate of x1, because x1 is the independent which depends on the x2 and x3. Okay, it depends on the x2 and x3. Okay, so the formula for this is summation under root of summation of summation, if you can say, sorry, it's 1.23 square is like summation xi minus x1 estimate whole square and divided by n. Okay, here you can see that x is one or est is the estimated value of x1. Okay, because here from here equation a, b and c, we are able to calculate the value of a 1.23, a12.3, and a13.2. Then after, our main equation is equation 1. That is, if you can see, you will find, if you can see, you will find our, suppose, for example, okay, say x1 equals a1.23. Suppose it's 0.54. Okay, plus a12.3, it's 0.44x2 plus 0.32x3. Suppose we have calculated and found the value of a11, sorry, a12.3, sorry, a1.23 is there actually. A1.23 is there plus a12.3 x2 plus a13.2 x3. So we have calculated the value and found out this value. Star equation is the modeled value. Okay. Then the estimate for the given value of x2 and x3 is x1 est. Okay. So x1 comma est is the those value from the model, and the actual value is xi. Sorry, x1, not xi is there. Sorry for this. Okay, so it's x1 minus x1 estimated value, and the difference then square then divided by n. This is the the uh, standard error of the estimate x1. Sorry, the variance of the estimate x1, and taking the under root, we will find the standard error of the estimate x1. Okay, similarly, we can solve if we have considered different random variable as a dependent variable. Now, the multiple correlation and the partial correlation. Okay. So here, like the coefficient of multiple correlation, the formula for the coefficient of multiple correlation is this, which is like R1.23. Okay. The capital one is for the multiple. Okay. And the smaller one is for the partial. Okay. So it is like 1 minus sigma square 1.23. Okay, if you can see here, the star equation in this is sigma 1.23. So sigma square can also be calculated and divided by sigma 1 square, the true value and the estimated value, obviously. Okay, and then taking the square root or power half. So this is the correlation coefficient, the multiple correlation coefficient. Okay, like in some practical situation, we need to study the correlation between the between one dependent variable and the one particular independent variable, keeping the effect of all other independent variable constant. That means we want the individual impact, the individual correlation of one variable on the another dependent variable, and taking or assuming the rest of the random variables as constant. Okay, so in that case, we need partial correlation, not the multiple correlation. Okay. So the partial correlation, for the formula for the partial correlation is like R, like small is there, small r 12.3. So that means the partial correlation of the random variable 1 and 2 when 3 is keeping constant. Okay. So that is it's r12 is there, the correlation coefficient between the random variable x1 and x2 minus r13 into r23, the correlation coefficient between the random variable x1 and x3 into the correlation coefficient between the random variable x2 and x3. Okay, and then divided by it's 1 minus r13 square, 1 minus r23 whole square. Okay, so this is how we calculate the partial correlation coefficient of between the random variables x1 and x2, keeping the x3 as a constant. Here you can see is the partial correlation coefficient between x1 and x2, keeping x3 as constant. Okay, now there is a relationship between the uh, m- multiple correlation coefficient and the partial correlation coefficients, and this relation is given with the help of this particular 1 minus capital R 1.23 square equals nothing but 1 minus R12 square into 1 minus R13.2 whole square. Okay, so this is the formula here. Capital R is for multiple correlation and small r is for partial correlation. Okay, so we can, like, if we are given one correlation coefficient, then we can calculate the another one. Now the next is the numericals. Okay, so here we are given the table that shows the weight and the height of age of 12 boys. Okay, we are given 12 group actually. The weight x1, height x2, and the age x3 is there. So we are three random variables actually. Okay, weight, height, and age. Now the first one is find the least square regression equation of x1 on x2 and x3. Okay, so that means we need to find x1 on x2 and x3. That means x1 is a dependent random variable and x2 and x3 are independent, or x1 is regressed and x1 and x2 are regressor or explanatory random variable. Okay, so okay, so let me write here x1 equals, like here you can see actually, but let me write here 1.23. Actually, we have already discussed in the above, if you may remember. These are like this line, the equation one is there. Okay, so this equation one is actually we are writing. So it's b 1.23 plus b 12.3 x2 plus b 13.2 x3. Okay, so this is the regression line. This is the regression line of x1 on x2 and x3. Okay, so this is equation one hour. Okay, or the equation is star. Let's consider the equation is star. We need to find the least square regression equation for this. So we need to find the least square regression equations. So that means what? That means we need to find the normal equation. Okay, so here you can see from there, if you are remember the here as we construct equation A, B, and C with the help of equation one, the same approach is using here, the same concept we are using. Then the first one is summation of x1, the summation of x1, and summation of b 1.23, which is and this, and then b 12.3 summation x2 and this. Then multiply by x2 in equation star. Okay, then x1 x2, then summation of x1 x2 is there, b1.23, then b1.23 into summation of x2. And in the third equation, if we can see, this is like equation A that we have already discussed. Equation B is this, equation C is this. In the C, we multiply with x3 in equation star and then taking summation, and we'll find out this. So this is our normal equation actually. This is our normal equations. Okay. Now we have three equations and three variables. Three unknowns are there: b1.23, b12.3, and b13.2. Okay, so we can solve with the help of any software. Okay, and then also, yes, we are given data actually. Sorry, we are given data. X1, X2, and X3 are given data. So putting the values like summation x1. Summation x1 is what? X1 is weight. So the summation x1 is 64 plus 71 plus dot dot plus 68. So once we are able to sum, we can find out it's 753 actually. The sum is 753. The next sum is like, okay, summation x2 is there, which is like 643. Okay, it's 643, and age is x3 is there, which is like 106. Okay, we are the sum of these three variables, and since we are given 12, so we can like the x bar is like, sorry, x1 bar is like 753 by 12. We can simplify those values. Okay, so with the help of those we can solve, or no, we don't need actually those things. With the help of here only, we are three equations in three variables. With the help of any software or by manually, if you can solve, you can solve, and you will find, uh, we are given the solving this value. We are given b1 dot this, this, and this. Okay, so these are the regression coefficients. So our regression equation will be like what? Since our regression equation will be like x1 equal to like b1 dot 23 is there, plus b12 dot 3 x2 is there, plus b13 dot 2 x3 is there. Okay, so we have already estimated the values of b12 1.23, 12.3, and 13.2. Putting those value, we are able to construct the regression equation, which is given in equation 6.12, and this is the uh, enclosed equation. Okay, so this is how we like proceed when we are given and we need to calculate the least square regression equation for the one variable with respect to the another two or more than two random variables. Okay, the next is determine the estimated value of x1 from the given values of x2 and x3. Okay, okay, here like we are given in this question, we are given weight, height, and age. X1 is the weight. So in question second, we need to estimate the value of x1. Okay, and how can we estimate? We can estimate with the help of the model we have created in the first part. Okay, so here in the first part, we have created the 6.12 equation actually. Okay, we have created x1 is this. Okay, so the estimated value of x1 is what? The estimated value of x1 is like we consider x2 and x3. Okay, in equation 6.12, we put the value of x2 and x3, that is height and the corresponding age is we put there. Okay, and then we estimate the value of x1. Okay, so just we need to solve those 12 number of times actually, putting the values of x2 and x3 and then solving, we will find out the estimated value is this one, and this is the given or true value. So here you can see that like for x1 equal to 64, the estimated value is 64.414. Or the x1 like here, you can see the actual value is 77, but the estimated value is 65.717. And here also like any value like here, it's 58 is there, so 56.925. So at some point there is a some distance between the estimated value and the actual value. But with the some other numbers, there is very less difference between those numbers. Okay, so this may happen. Okay, and this is the error actually. Okay, so the next question is like estimate the weight of a boy who is 9 years old and 54 inch tall. So here we are given 9 year old, 9 year old, that is x3 is given. So we are given x3 is 9 and inches. Okay, height is x2 and x2 is 54. So with the help of those model, 9 and 54 is there. So in equation 6.14, put the values of x2 is 64, sorry, 54 is there, I think 54, and x3 is equal to what it is this 9. X is 9. We can calculate the x1, the estimated value of x1, which is like here it is already given actually. This is given, and putting those values in equation 6.14, we after solving we will get like 63.356. So that means what? So that means if a boy of like weight, okay, x2 is the weight na. Let me check once. Height, x2 is the height and age. Okay, so here a boy of height 63 inch, 63.356 inch, and a age of 9 years. Okay, then its average weight is approximately 63.356 kg. Okay, so this is how we predict with the help of the correlation and regression analysis. Okay, the next question is because we have created a model actually. Okay, the next is compute the standard error of estimate of x1 on x2 and x3. Already we have a simple formula, putting the values. Okay, putting all the values from the samples, and after solving we will get 4.6 as the standard error. And the population standard error is like under root of n upon n minus 3 times the standard error of the estimate, which after calculation is 5.3. This is the formula actually. There is nothing like logic. Now the next is compute the coefficient of linear multiple correlation of x1 on x2 and x3. Okay, there is linear multiple correlation. There is multiple correlation, that is capital R is there. Okay, so let's okay, capital R, x1 on x2 and x3. So R1.23, which is with the help of this formula comes out to be 84.18%. Okay, and we have also like able to calculate the partial correlation coefficient. Okay, so the partial correlation coefficient is 53 for 1 on 2. The correlation coefficient of between x1 on and x2, keeping x3 as constant is 53%, and x1 and x3 keeping x2 as a constant is 48%. So that means what? That means 1 and 2, like x1 and x2 are slightly slightly more correlated as compared to x1 and x3. That's why it is a partial correlation. The correlation between the two random variables, keeping the third random variable as a constant. Okay. So here it is 53% is 45%. So there's a slight difference between the association between the random variable x1 and x2 as compared to the random variable x1 and x3. Okay. So then, okay, sorry. Okay, yes, we have one more question actually here. The question is like compute the coefficient of linear linear partial. We that are already calculated actually. The F part. Okay. Okay. Now the next topic is regression. Okay. So like in simple linear regression, that is the formula for this. Okay. Suppose it is a simple linear regression. Okay. So we have a linear statistical format. Okay, statistical form. So here there is an error actually. This error is like E or epsilon I or EI, whatever you may write. Okay. So in simple linear regression, we have a relationship of the form 6.13, which is yi, which is dependent variable, is depend on the linear, which is a linear combination of the independent random variable xi with some unknown constant. That unknown constant are called regression constant, the coefficient of regression. Or okay, here like y is the random variable and xi is another observable variable. So these are observable random variable, are also called independent random variable or explanatory variable. Okay, and here the quantity beta naught and beta 1 are the intercept and slope. As you can see, you already know, no, like y equal to mx plus c is there. So c is the slope and m is the intercept. Sorry, m is the slope and c is the intercept actually. So in the same way, if you can like compare these two things, the beta naught equal to c, which is nothing but the intercept, and the beta 1 correspond and together with like xi is the slope of the regression line. Okay, which are unknown. These beta naught and beta 1 are unknown, and our aim is to estimate these beta naught and beta 1. Okay, now here EI also one more assumption is there actually. Here EI is a necessarily random variable. Okay, it is an error variable actually. Okay, and it is a such type of error in which like the expected value of these error variable is nothing but zero. Okay, that is already written here. And our expectation of epsilon I is zero. Now with the help of the equation 3, okay, if we take the expectation, then expectation of yi equal to expectation of beta naught. Since beta naught is unknown but constant, so the expectation of beta naught is beta naught itself. Okay, then expectation of beta 1 xi, the beta 1 is like taken outside from the expectation, so it is beta 1 expectation of xi. Okay, and expectation of epsilon, so expectation of epsilon is nothing but zero, that we have already assumed, or we have one condition. So now note that the function that gives expectation of y is a function of x, and it is called a population regression function. Okay, so it is a population regression function. Okay, the 6.14 is nothing but the if you can like see the equation, this equation is nothing but the population regression function for the simple linear regression. Linear regression is because there is only linear association between the dependent variable and the independent variable. Okay, and we can write these like this: the fact that our inference about the relationship between xi and y, sorry, yi and xi, assuming knowledge of xi, that means xi's are independent. We know the xi's and we study about the impact of xi on yi. Okay, so there are conditions that we know. Okay, so that's why the expected value of yi given xi, which is beta naught plus beta 1 xi, because it is a sample property. When we have different sample, it may have different results. Okay, so this is the regression, simple linear regression. Now the next is like here we have the dependent variable and the independent variable is there. Okay, like yi is called the response variable. Okay, it is called the response variable or the dependent variable, whereas xi is called the predictor, which is used to predict the values of dependent variable, or it is also called independent variable. It is also called explanatory variable. It explains the yi actually. The xi is the variable which explains the yi, so it's explanatory variable as well. Okay, also recall that the word regression in connection with the conditional expectation, that the regression of y on x is defined on, okay, regression of y on x is given there. Okay, the x is given there, so that's why it is expected value of y given x. That is the conditional expectation of y given x equal to small x. Okay, now in general the word regression is used in statistics to signify a relationship between variables. Okay, the regression means we make a model which make a relationship between the independent variable and the dependent variable. And with the help of those independent variable, we are able to predict the dependent variable. Okay, that is the regression actually. Now the regression is linear. Okay, the above equation actually, we are talking about this equation 6.15. Okay, so here this equation concludes the regression is linear whenever xi is fixed and unknown. Okay, here xi is fixed and unknown. Here xi is degree 1, so it is a linear in nature. Okay, and it's realization of the adjacent random variable xi. Note that if we assume the pair of xi has a bivariate normal distribution, it immediately follows the regression of y on x is linear. Okay, so these are some of the topics related to this. Now, how to like estimate the those sorry, how to estimate those regression coefficients. Okay, so that is used with the help of least square methods. Okay, and in least square method, the residual sum of square. Suppose we are given a line like y equal to c plus dx, or y equal to mx plus c kind of line actually. The c is intercept and the d is the slope. Okay, so here y is the dependent variable and x is the independent variable. Okay, so the residual sum of square is what? So it is yi minus of c plus t of xi. The difference between these values and then taking the squares. This is the residual sum of square denoted as RSS, residual sum of square. Okay. Now, the least square estimates of beta naught and beta 1 are defined with the help of those values of a and b such that the line x actually the least, here the word least is already there. Na? The word list is already there. So that means we have a different values of C and D for which this summation, this RSS is minimum. Okay. So those value of C and D for which the RSS is minimum is, we have taken A and B. Actually, those are the estimates. That means A and B is the estimated value. Okay. So the least square estimates, here we can also see that the minimum of CD, if you can see, the minimum of CD. Okay. Okay, sorry. Here. Okay. So minimum of CD. Okay. For which this summation is okay. The value of CD for which this summation is minimum is nothing but A and B. Okay. The values of C and D for which this summation, the residual sum of square, that means is minimum is A and B. So now we need to calculate this with the help of like least square estimate that we have discussed above. Okay. After solving, we will find out how to like find out these things. Is there anyone who know about how to calculate this? How to find like the beta naught cap and the beta 1 cap? Is there anyone? Okay. Am I audible? Na?
Yes, sir.
Yeah.
Okay. So here, like we can see actually, if you just wait. Okay. Here, this is like we have a this RSS. This RSS. We need to like differentiate this with respect to the parameter. Okay. Then first differentiate this with respect to the parameter, and the next is equate it to 0. And then we have like optimizer value. Okay. And then we will further verify whether it is a minimum value or the maximum value, and then we can calculate the estimated value of those uh, regression coefficients. Okay, like here, if x is the predictor value and y is the response variable, and we think of predicting y from x, then the vertical distance measured in RSS is reasonable. Okay, so this is how the least square method works. Equation 1 is RSS. We differentiate with respect to C and D and equate it to 0, and then calculate the value of C and D. Those are the estimated value actually. Okay. Here C and D and A and B and beta naught and beta 1 cap are kind of similar thing. Okay. C and D is the general term. The minimum value of the value of C and D for which the RSS is minimum in A and B which is also nothing but the beta naught cap and beta 1 cap respectively. Okay, so these three are like similar value. So don't get confused with those different variables. Okay, C and D is nothing but C is equal to A kind of, and A is nothing but beta naught cap. Okay, and the similar for D. Now the next is there is a question actually. The question is, it is expected that y is linearly related to x. Determine the least square regression line uh, for uh, regression line for expectation of y on the basis of 10 observation given in period this. Okay, so here again we don't need to do anything actually, since it is already solved. But let me we are like what, y equal to beta naught plus beta 1x. This is the question. Y equal to c plus dx, or y equal to beta naught plus beta 1x. Okay, similar. Uh, then residual sum of square is there. Okay, like here in equation 1, yi minus c plus dxi. Okay, the similarly here uh, we can calculate. Okay, and then with the help of those we are able to find out beat star equation star beta naught cap and beta 1 cap. So beta naught cap is what, y bar minus uh, here b is nothing but like beta 1 cap, beta 1 cap x bar. Okay, and beta 1 cap is like sxy upon sxx. Okay, so now the sxy is what, uh, this quantity is xxy and this quantity is sxx. We have already the value of this, the value of this, so it is approximately 0.57. Okay, so beta 1 cap is here 0.57 is there. Okay, now with the help of 0.57 we are able to calculate the beta naught cap. Okay, so beta naught cap is also there, which is like 17.03. So we have the estimated value of the correlation, sorry, the regression coefficient. With the help of this regression coefficient we put in, so we find y is nothing but 17.03 plus 0.57 times of the x. So this is our least square stream. Okay, so this is the least square regression line. Okay, now we can put the value of x, and on the basis of those value of x we have the estimated value of y. Okay, now the next is multiple regression equation. Now since we have discussed about linear regression, okay, linear regression, now multiple regression is there. Okay, so it may possible like in simple response variable, suppose we have a response variable y, which is dependent variable obviously, and it depends on a number of variable, a set of values of inputs. Okay, the number of independent random variables. Okay, like x1 x2 and those. So these are the multiple regression equation. So this is the form of the multiple regression equation. Okay, beta naught plus beta 1 x1 plus beta 2 x2 plus dot dot plus beta r xr. So there is multiple regression coefficient is there. In the above, we have only one regression coefficient, and the one is the slope. Sorry, intercept. The another one is the slope. Okay, so in multiple regression coefficient, there is multiple regression coefficient is there. Okay, multiple regression equation, there is multiple regression coefficient, and we follow the same approach since it is a like very tedious job to estimate the parameter of all those, but the same process we will follow. Okay, then the even in the first one actually here like a simple linear regression model, here we have calculated the beta naught cap and beta 1 cap. Okay, now we can check, we can check the unbiased estimator method also, that is the least square estimator. Okay, that is the least square method. With the help of those we are able to estimate the regression coefficient beta naught and beta 1. Similarly, there is more methods like unbiased estimator method. We have a simple linear equation. We have a simple linear regression equation like this. Okay. So again, with the help of, there are some assumptions, obviously, like the random error are assumed to be independent normal random variables. Okay, having mean zero and variance sigma square. Okay, and then after solving with the help of those method, our beta 1 estimate, the unbiased estimator of beta 1 is like this 6.19. Okay, it is summation of xi minus x bar into yi and divided by summation of xi square minus x n into x bar square. Okay, this now, is it unbiased or not?
हेलो हेलो सर आवाज नहीं आ रही है